Good afternoon, Professor.
Hi, nice to see you. Okay, hello guys. So we continue today talking about uh, molecular theory of ideal gases. And today we will sum up this topic. So next week we will dedicate to entropy and second law of thermodynamics in order to finish and cover as much as possible all material which will be considered for the final exam. So last discussion we introduced the concept of molecular heat capacitance, which was defined for different processes, in particular for isovolumetric and isobaric, isobaric process. So when we have constant volume and constant pressure. So there is a difference between these two molecular heat capacitance because there is some work done during the isobaric process, and that's why we have some redistribution of a total change in internal energy. However, in the process with constant volume, we just deal with only with heat, like energy transfer by heat. Work is not done. That's why total change in internal energy is equal to the heat total energy transferred by heat to or from system through its boundaries with environment. So now also we introduce this adiabatic process and figure out the relationship between main state parameters of ideal gas during a adiabatic process. So in particular relationship between pressure and volume, and also temperature and volume. So based on this adiabatic process in ideal gases can be analyzed. So our next step, I mentioned it several times, and now we're coming to this point when we need to consider the molecular structure itself. So far we were dealing with monoatomic ideal gases, and now we need to consider an option when we have multi-atomic, in particular diatomic, like two atoms molecules. They are also multi-atomic molecules, and we will see what kind of unique features it brings to specifically to molecular heat capacitance by making molecular structure more complex. Okay, now I will switch to the slides and let us consider instead, so let's a bit maybe also remind. So far we were considered monoatomic case, and we have shown before during our discussions that in case of monoatomic ideal gas, kinetic energy of its molecules consists only from translational kinetic energy of translational motion. In this case, each atom possesses 3 degrees of freedom. And each degree, so total energy, like kinetic energy of this translational motion will be 3 second kT. So K is Boltzmann constant. And we figure out that each degree of freedom provides 1/2 kT. Taking this into account, we can proceed first. So now, instead of considering atom, like molecule in which forms an ideal gas in the form of some mathematical point, like point mass, we will consider it a system of 2 point masses. So we will have so-called diatomic molecule. And let us consider possibilities of its like summing up different kinds of kinetic energy for such system. So say we have some system of coordinates x, y, z. So this is our diatomic molecule, and it can participate in translational motion. So when they move, let's say along axis x, or doesn't matter. So the angle of orientation of this molecule doesn't change with respect to 3 axes of this system of coordinates. So we will have also translational, obviously we will have contribution from translational kinetic energy. However, if it's not just a point mass, but a system of 2 point mass, it can also participate in rotational motion. And we know from this chapter we discussed in mechanics, rotation of rigid bodies, that rotation also provides its contribution to total kinetic energy. So if we have another system of coordinates here, x, y, z, we have this diatomic molecules. So there are several options. So it can rotate about axis y in this direction. It can rotate about axis x in this direction, and about axis z in this direction. Since we consider that the size of atoms is negligibly small, and we deal with some point masses, then moment of inertia for this system about axis y will be equal to 0, because we neglect with the size of molecules. If it rotates about axis y, then moment of inertia about axis y will be equal to 0, and that means that the kinetic energy for such rotational motion, which is defined as 1/2 moment of inertia about certain axis of rotation times angular velocity square, will be also equal to 0. So this specific rotation will not contribute to total kinetic energy. However, it will not be true for rotations about axis x and about axis z. So they will contribute to the total energy, the kinetic energy. And another thing which should be taken into account, this is vibration, vibrational motion, which we also discussed. And we know that vibrational motion possess some kinetic, like if an object follows some vibrational motion, then it possesses some kinetic energy. So in this case, this diatomic molecule can be represented in a form of 2-point masses, which are connected with some string. This string is some representation of chemical bond between these atoms, and which actually forms the molecule. So there is some chemical bond, like some interaction between two atoms, and it will possess some, let's say, this equivalent of string coefficient. So if it is the case, obviously these molecules can vibrate with respect to its equilibrium condition, and this vibration will contribute also toward the total kinetic energy. Since total kinetic energy defines total internal energy of ideal gas, that is very important because by definition, specifically, we will consider process with constant volume, isovolumetric process. In this case, change in total internal energy will be defined by the change in temperature times specific molecular specific heat capacitance for isovolumetric case. And this, of course, should be taken into account when we have a transition from monoatomic to diatomic ideal gas. So we know that each degree of freedom provides energy of 1/2 kT. Translational motion provides 3 degrees of freedom. Since we can neglect with one rotational motion, which is about axis y, then rotational contribution of the atomic molecule will provide 2 additional degrees of freedom. So in total, it will be 5 degrees of freedom. And this vibrational, we will talk about this later, also will provide additional 2 degrees of freedom. So now let us focus first on this translational and rotational. So in this case, total internal energy will be equal to 3, which is 3 degrees of freedom for translational motion times n, which is total number of these molecules, times energy provided by each degree of freedom, 1/2 of kT. So this is what we get from translational motion. Let's mark it as T translational. Then we have additional contribution from rotational motion. It will be 2, because we have 2 additional degrees of freedom, times n, total number of molecules, times 1/2 kT. So this comes from rotational motion. Yeah, I don't know if you hear, but someone is doing some fixing and it's quite disturbing sound here. I'm sorry about that, but unfortunately we cannot control our environment very good. So now we look what finally we get. It will be 5 seconds times total number of molecules times kT. Or we can represent it in the form of ideal gas universal constant, which will be 5 seconds nu, which is number of moles of substance, times R, universal constant, gas constant, times T. So in this case, we already see that this total is internal energy, which is equal also, we can write here that it's total kinetic energy. In this case, it's equal not to 3/2 of kT, but since we have 2 additional degrees of freedom, it will be 5 seconds kT times, of course, number of molecules. And by definition, as we did on the previous discussion, now we can determine the specific heat capacitance at constant volume. So we know from previous discussion that this quantity is equal to 1/nu d internal energy over dt. So change of internal energy of the system with a certain change of temperature. And this will be equal to 1/nu d here dt, and here we need to put this expression of our internal energy. It will be 5 seconds nu RT, and as a result, we factor out this 5 seconds nu R, cancel out dt, we end up with 5 seconds R, which is different for the monoatomic gas, where we got CV, let's write here mono, equal to 3 seconds R. So means that capacitance, specific heat capacitance at constant volume for diatomic gas, ideal gas, is larger because we have additional degree of freedoms which will consume some energy to be activated. And that, of course, increases specific heat capacitance. So you see from this very simple and straightforward example how molecular structure, which is such a minor feature, which is on very small length scale, can be observed. It has a direct impact on macroscopical parameters of the material, in this case ideal gas, but that also matters for all other substances like solid state. So molecular structure, it is very important parameter which should be taken into account in order to predict some macroscopical features of the system based on these molecules. So now let us proceed further and contribute, take into account the contribution of vibrational motion. So let's go to another slide. Or maybe before we do that, let's come back here. And I mentioned this before already, but I believe it worth mentioning here too, that this relationship between Cp and Cv, which is Cp, specific heat capacitance at constant pressure minus specific heat capacitance at constant volume, is equal to R, which is universal gas constant, is valid for all types of molecules. So regardless if it's monoatomic or diatomic, because this difference is caused by the work done on the system, and this work is not dependent on molecular structure of the gas. That's why this equation is valid always, and that's why according to this equation we can calculate Cp for diatomic gas will be Cv plus R, and this will be equal to 7 second R. Okay, so now we define C values for Cv and Cp, specific heat capacitance for constant volume and pressure, taking into account rotational motion of the atomic molecule. So if we proceed further and also take into account the contribution from vibrational motion, so we need to consider total internal energy now. So again, 3 degrees of freedom for translational motion, plus 2 degrees of freedom for rotational motion, and additional 2 degrees of freedom for vibrational motion. V1/2 kT. And in total, taking into account this relationship with the nu and R, we can write that will be 7 second mu RT. So it's already getting higher and higher. That's why we can show that Cv, specific heat capacitance at constant volume, for the case when we have contributions from translational, rotational, and vibrational motion, will be equal to 7 second R. So now it is an interesting moment. Why do we consider, let's say we have two atomic molecule system, some ideal gas, then we know that these vibrational and rotational contributions should be there. So why do we consider still separately translational motion, translational with rotational, and then translational, rotational, and vibrational? So from first point of view, we should just go to the last point, consider all of these contributions, say, okay, this is the value for the atomic system. However, it's a bit more complicated. And the main reason for that is that energy levels of molecules, specifically rotational and vibrational energies of molecules are quantized. Means they are not changing continuously. There are some quantums of like discrete energy which the system can, like molecule can possess. So its energy can change not continuously, but kind of like a step like. Taking into account these features of molecules, that rotational and vibrational energies of molecules is quantized, the capacitance, specific heat capacitance of ideal gases with, let's say, diatomic molecules changes with temperature, also like step-like. So it will be something like this. Let's say we have temperature in Kelvin. Let's change it so it will be logarithmical scale. Let's have 10, 100, maybe 200, then I don't know, 500, 1000, 2000, and so on. So we have some logarithmical scale on this axis, and here we have just linear scale for specific heat capacitance. So if we have the atomic ideal gas, its CV, like specific heat capacitance as constant volume, will not possess just some single value, which is, for instance, this one, for all temperature range. It will change with several steps. So at low temperature region, we will get value for heat capacitance, like molecular specific heat capacitance, CV, 3 second R, which is the case for monoatomic gas or only contribution from translational motion, which is surprising because we deal with the atomic system. However, when we go to higher temperatures with some step, this value for the molecular specific heat capacitance will jump up and saturate again. And this saturation will be observed at the value of 5 second R. So this is when we have contribution from translational motion plus rotational motion. And then when we increase temperatures to even higher values, which is, you see, it's already above 1000 degrees, 1000 Kelvin, that is very high temperature. And at some point, at very high temperatures, we get third jump up and saturation. And this will be 7-second R. So in this case, we already have full contribution of possible kinetic energy types of the atomic system, which is translational, rotational, and vibrational. So why it happens? Because we, as I mentioned before, and rotational and vibrational energies of molecules are quantized, and that means you need to activate with enough energy these type of motions in order to have their contribution to the total kinetic energy of these molecules. So initially we have contribution only from translational motion, which is not quantized and always present. Then we increase temperature, we provide enough energy to activate rotational motion. Then we have a transition from of specific heat capacitance to the case when we have contribution from rotational motion, and then it increases further because of higher temperatures and activation of like higher frequencies of vibrational motion oscillations, and that will result in experiencing contribution from all types of kinetic energies, which is translational, rotational, and vibrational motions. That's why it makes sense to consider step by step contribution of these mechanisms, since they may be observed in different temperature ranges when we consider such ideal gases. Okay, so with this, we are already finished, and we have another topic to discuss, which is distribution of molecular speeds. So far, we were considering some average velocity, some average speed of molecules in ideal gas. However, we know that ideal gas, we consider this like model of ideal gas. It consists of very many particles, and they all move extremely chaotically. So this motion, their motion is very chaotic. And that means that there are different possibilities for interaction via collisions. So there is a chance for a certain type of sequence of collisions, which will increase significantly kinetic energy of certain molecules, or in contrary, decrease kinetic energy of certain molecules with respect to the average value. And that will result in some distribution. So we will have some energy distribution of a number of molecules which possess these kinetic specific, some kinetic energies within certain range from, let's say, K plus like K to K plus dk. So this is some interval of kinetic energies, and within each interval of kinetic energies, we will have some certain portion of total particles which form ideal gas, which will possess these kinetic energies. So in order to take this into account, like quantitatively, there is such so-called number density function, and V as a function of energy. So which by definition, the product of NV as a function of energy times dE, some energy interval, will give us the number of molecules per unit volume with energy between E and E plus dE. So this is the function which tells us how many per unit volume molecules will possess energy in this interval. If you change energy, you go to E prime, then it will be NV E prime dE, and then the interval will be different. It will be E prime to E prime plus delta dE, and in this case we will get different number. So this number of particles in the unit of volume will depend on energy, and this distribution for general cases, it's very broadly applied, and you can meet it in different fields. However, like of statistical mechanics, where we deal with many systems of many particles, and in particular also for the ideal gas, this is so-called Boltzmann distribution, and quantitatively is given as this equation, NV as a function of E equal to N naught exponent minus E divided by KT. So this is Boltzmann distribution. So here N naught is the number of molecules per unit volume, which has energy between E equals 0, so from 0 to energy equal some dE. So it's also the same interval, but this interval calculates not from some energy different from 0, but goes from 0 to dE. So definitely it will be, since all particles want, like in all systems, always want to get minimum energy, go to ground state as much as possible. So the concentration of particles in this interval from E0 to E equal dE will be the biggest. The most particles will be in the vicinity of this ground state of E equals 0. However, if we increase energy, we exponentially will reduce the chance, like number of molecules per unit volume, which will be in interval from E to E plus dE. So here we can write 0 plus dE. So this is the highest value when we consider N naught. But for all other energies, we can use this number density function and this equation, which is given as Boltzmann distribution, and that will help us to calculate concentration of number of molecules per unit volume, which is concentration of molecules which possess energy from E plus to E plus dE, and we can select any energy. So obviously, if we select some very large value for E for energy, and we have exponential function here with minus, obviously will be very little amount of molecules which will possess this high kinetic energy in the range E to E plus dE. So now this is about energy, but also it's important to know how speed of molecules is distributed. And based on so let us think about this distribution, how it should look like. So let us consider how many molecules from the system will possess a speed in the range from v to delta v. So we need some distribution of speed for molecules, and then we can determine how many of these molecules per will possess this speed. So it is obvious that maximum of this distribution should be somewhere in the vicinity of so-called RMS. So which we defined previously, it's a square root of the average square velocity. And since it's some kind of average velocity specifically determined, it should be somewhere close to the maximum of this distribution. And this distribution can be shown like this here. It will be axis for speed. Then it will be some nv, which is like number of defines number of molecules which will possess certain speed, and it's called some Maxwell-Boltzmann speed distribution function. It will be not symmetric distribution, something like this, because at zero velocity we have no molecules, and there is no limit for maximum velocity which particles can possess. So this is kind of extended to the right. And our VRMS will be somewhere here. It's a value which is a bit larger than so-called most probable velocity, VMP, and average velocity will be somewhere here in between. So we will give equations for these velocities, so you can use them for solving problems later. V average. So the function, this Maxwell-Boltzmann speed distribution function, is NV equal to 4P, N total number of molecules, M naught 2 pi KT in the power of 3 seconds times V squared times exponent of minus m naught v squared divided by 2 kt. So we see that it's kind of complicated function, but what is important that it depends also on, like, exponentially depends on temperature, and the effect of temperature will be seen by broadening this distribution. So if we have let's say N, V, then V here for one distribution. It's the same system, but this distribution is at 300 Kelvin. Then if we increase temperature, something like this, this distribution will become broader and maximum will decrease. So so-called most probable speed will be shifted to the higher values. And this distribution will be broader. So this is the effect of temperature. Let's say it will be at 900 Kelvin on the Maxwell-Boltzmann distribution of for speed of molecules in ideal gas. So now we can introduce three characteristic speeds, which are important in kinetic theory of ideal gases. One we already know, this is VRMS equal to square root of V average, V square average, and this is equal to 3 kT divided by m naught equals to 173 square root of kT divided by m naught. Then second characteristic velocity is average velocity, and this is equal to square root 8 kT divided by pi m naught, and this is 1.60 square root kT m naught. So we see that it's slightly smaller. And there is one more, which is defined by the position of maximum of this Maxwell-Boltzmann distribution. This is V maximum probable velocity. It is equal to square root 2 kT divided by m naught equal 1.41 square root kT divided by m naught. So these are three characteristic velocities for like speeds for ideal gas and like molecules which form ideal gas. And it worth to mention that similar distributions of energy and speed of molecules is also valid not only for ideal gas, but also, for instance, for liquids. So at some temperature, which is, let's say, 300 Kelvin, there is, it's much lower than the boiling temperature and like room temperature, but we still have certain amount of molecules of water which possess enough kinetic energy to overcome the attraction of the bulk of the water and leave the surface of water. So we get some evaporation of water even at temperature which is much lower than boiling point. And this is because of this distribution of molecules per velocity, like speed and kinetic energy. And since some highly energetic particles leave the system, they bring with itself some part of internal energy of the system. And that means that most of low energy particles, they remain in the system, these molecules, and the internal energies of the total system reduces, it causes reduction in temperature, so the system cools down. That's why when we come out from water, we feel quite cold because of evaporation, and in total this system cools down. We had some reduction in temperature. So the definition, the way how we can determine total number of particles with within certain interval of velocity. We just pick up, for instance, some v. Here is v plus dv, and the area of this distribution will give us the number of particles which possess velocity from v in the interval from v to dv, and this will be equal to n v, this Maxwell Boltzmann distribution function, times dv. So if we integrate for larger intervals, we can get the answer on how many particles of this system possess speed in the range from v1 to v2. Okay, so this is pretty much everything I wanted to tell you about this kinetic theory of ideal gases. Please pay also attention to textbook. We cannot cover all topics here in details, but I'm really trying to discuss with you as much as possible within our time frame, and in order to prepare you for some last topics in the thermodynamics, we will continue our discussions next week. If you have any questions, you're welcome to ask, and yeah, actively try to prepare for the final exam, which is coming quite soon. So that should be your one of your top priorities. Okay, guys, thank you very much for attention. Have a good evening and good weekend. Don't waste your time and prepare for final.
Excuse me, Professor.
Thank you.
Yeah.
Can I ask a question?
Yes, sure.
At the beginning of the course, we someone asked the question about the office hours, and I think we forgot to ask it again. And
oh yeah, we actually we discussed this. So taking into account this format of online teaching and the concept of flip course, we're supposed to have all our discussions as kind of office hours, because we don't monitor students' attendance. We are kind of supposed to answer questions from students which they have during reading the textbook. However, practice has shown that there is like very limited number of questions, and that's why I decided to provide more material discussion during these lectures. And that's how we combine our lectures with office hours, because it's all kind of discussion of the material which is supposed to be processed by students at home with the textbook or some videos.
now I got it. Thank you very much.
Yeah, so if you have some questions, first of all, there is an opportunity to revisit all our discussions because they all are available on Moodle. I try to upload them immediately after our discussions, so all these videos are recorded Yeah, and in order to give you a chance to have some, to hear some explanation of this concept from my side, I would also like to continue our discussions next week. It was considered by syllabus as some already recall of previous material. However, I think that you have access to all our recorded discussions, and that's why it's better if I provide you my vision of this topic, entropy and second law of thermodynamics, during next week. So you have a chance to get some feedback from me on this topic, and hopefully it will help you somehow better to prepare for the final. Okay, thank you for attention. Have a good weekend. Take care, guys. Bye.
Thank you. Goodbye.